All right, welcome to the Unit 6 webinar on space and the universe. We're going to jump right into the learning plan. And worth mentioning, here's that idea capture tool that we just mentioned. I'm going to go ahead and close that. Course attendance, if you want to check that. Okay, the overview. This is just 3 tasks. So here is some earth science and physics in Unit 6. That this can, you got a couple of, well, here, I'll quick overview the task. Halley's Comet to contextualize universal gravity. Then we have using the cross-cutting concept energy to connect prior learning in the course to orbital motion. And then just a really fun one, but a also ambitious performance expectation, construct an explanation about the evidence for the Big Bang theory. Want to just call out that each of these are about 2 days, and you have the option of you can end the year on them. In fact, that's how we will be ending our year. Or if you have like 2 days before winter break and you don't want to lose them and you've kind of wrapped up a unit, or you have 2 days before spring break, or just these little spots where 2 days fit in, these can fit there. So many years we have done exactly what I just said. 2 days before winter break, we did one task. 2 days before spring break, we did one task, and then finished the last task on the last 2 days of school. So, of course, they have an ideal placement. So, for instance, Halley's Comet after Unit 3, which is engineering a shoe that involves forces. Of course, it's really nice to do Halley's Comet after that. But students do have a feel about forces from middle school, just everyday life. So these really can be placed, but each task does have an optimal placement.
And then the other thing is just recommended that going in the order of Halley's Comet, the orbital motion and Big Bang, um, just because at least the first two build off of each other a little bit.
All right, so we want to dive right in, and being a webinar, just want to blast you with touches at each of these important steps. So that first one, the phenomena, Halley's Comet, is and of course we got just that question. Have you ever heard of Halley's Comet? What comes to mind when considering connections of comets, outer space, and human society? There is a video here by narrated by Leonard Nimoy of Star Trek fame, and we are going to show mini videos, but I don't think this one makes the cut. But just a chance. It's a hook, and a lot of students like it. And then, of course, not everyone likes that though, but just a hook. It's fun. There's videos. And now we want to jump into giving you some background that here is uh, a series of photos of taken by a taken on an actual comet here, Comet 67P. And it does look like snow, but reading about this GIF, that is actually like cosmic rays showing up on the film versus like snow falling on the comet. And we're going to just show a couple of these slides. And oh yeah, I meant to go back to the agenda to anchor us, but I'll do that at the end of this here. All right, so a little bit of background about what's the difference of mass and weight. And of course, talking about space, that's a great time to contextualize that. Although we're going to show just about 45 seconds.
They're part of action and sci-fi meteors, and meteorites.
Okay, yeah, just wanted to get that. You can just see that it introduces these terminologies and hey, what is different about a comet and an asteroid, meteoroids, all of that. That is good stuff. And then just to be assuming some familiar with Halley's Comet, but we learned a lot when we decided this as the phenomena, but it is the only regularly returning short time period comet. So like within human society, it is the only comet to come back again and again. Clearly, other comets have come, but they usually don't return again in the span of human society. And so we got, these are just some of those earliest photos, 1986, which maybe some teachers might remember, but no students will. And then here is one where you really just see this little bit more dark smudge in the middle there is Hubble, but being, the surface being black and really hard to detect that in when it's not being lit up by the sun so well. And then here's just sort of a timestamp of the different spots. So it could, students always figure out where is it now, 2025. So really far out. And then of course, how old will I be when 2026 and it returns? All right, got a couple more just to show it. Short period, meaning like there are comets that might return on the 100,000 or 300,000 year time scale or million year time scales. But this is the only one short term visible to the naked eye. We weren't going to do all of these, but 18, but I'm not sure what slide I'm on right now. So I'll just say there's three more that will show retrograde. So it's weird, right? It's going the opposite direction than the motion of all of the planets. It's not in line with the solar system. And so it's out of the plane, which is also kind of neat because our solar system itself is out of the plane with the Milky Way galaxy's plane. And that's just another, each one of these little things kind of lands, like, whoa, you can get a few students that are totally surprised to think about that. Like, kind of have this assumption lots of times that we even get that question, and it's kind of in the research too, that like they know the solar system has a plane and it's flat, and the idea is like is the whole universe on that? Are all the galaxies on that plane with each other? And so this is just a great slide to show that. Okay, so I'm going to go back to the agenda so that we keep orienting back to the same spot. So just did that building common background, and I'll hand it over to Matt to talk and introduce us to the Desmos activity that accompanies this.
Yeah, thanks, Bradford. So big idea is that this is equal parts trying to introduce a new pattern, mathematical pattern, in this case is inverse squared, which is combination of square and inverse. But also equally inspiring to like inspire awe, like just really interesting thinking about, big ideas. A lot of students love astronomy, and then just engaging in like this opportunity to think about cross-cutting concept of scale and proportionality, like thinking about how these vast distances that we're going to be examining, how we can use those. So, but if you could go back to the slides and you'll flip forward a couple, I think just to the research question. Just our research question, how does the distance of the comet affect the force of gravity that's there? And so looking at the comet at various distances and seeing the force of gravity at those different spots, and just looking at these three different pictures as it's been traveling through space at different distances. And so in this one, it's really taken a lot of the stuff that we learned from distance learning and put into the Desmos classroom, just as a activity that's built in, that's really built for this. So if you don't mind clicking on the next tab over. And this is just starting to flex our our science tool belt, just looking at our research question. What do we think is going to be happen? They don't have a lot of experience with this over vast distances, but there is just a lot of intuition that as the distance gets further, that the force of gravity likely is decreasing. So they start with that intuition and then building from that intuition off of that into the data mining, which is on the next slide. Yeah, so in this one, this is meant to be a lot, and this is meant to be, this is just one slide, but this is some time. So students often are going back and forth between the last slide and this one is what data do we need to be able to answer our question, and just bringing up that idea of data mining, that there's a lot of data out there, and we have to be able to like pare down and decide, what do we actually need for this. And so in this case, they can circle on there, and we're looking at really the distance from the sun. That's like that third column, and the force between the Halley's Comet and the sun. So trying to get students to parse out what in the data is the most important, and highlighting those two columns and seeing what is there. Because the data is so big, on the next slide, go ahead. We populated. They won't have seen this before, but they're looking at those distances, and those distances are in AU, which is like a distance between the Earth and the sun. And like they've seen many times before, we're looking at for the best pattern, the simplest best fit model that fits all the data points. And so this one has that extra pattern that they have not seen before in inverse squared. So Bradford, do you want to talk a little bit about just differentiating between inverse and inverse squared, and how they're finding that model?
Yes, there's a lot of slides, but we know on the webinar not to flip too often back and forth. But there are slides that also give you guidance and visuals to be talking. But it is, we want them thinking inversely proportional. It's somewhat similar to that in the hypothesis stage. And then here they find you just can't get the green line, inversely proportional to work. So if I go and capture the last points, it's way off on the data points on the left. If I bring it up to capture those, it's getting way too high for these bottom ones. And that's of course because universal gravity is not inversely proportional with distance. It is inverse square, or a more familiar terminology that we use with students, and we'll show the slide, is inversely quadratic, but we do want them to know that in their textbook and everywhere else, they'll see it called inverse square. But in any case, so they have that here. I am going to bounce to the slide to show a couple of them. So here's just a really helpful slide, a snapshot of the graph, walking the triangle. This is the new slide that we're pairing with all of the posters, and that coral response has been a big success. And this is actually super fun because it's a new one, and it combines the quadratic language with the inversely proportional. Some things in this world, like gravity, when the distance gets twice as big, two things happen. It gets spread out twice as wide, it gets spread out twice as tall. So again, going back to quadratic here, but it actually gets, and then we do that count 1, 2, 3, 4 times smaller. So it's quadratic, but oppositely. So we call this pattern inversely quadratic, or again, textbooks and a lot of other places is going to call it inverse square. And so just got a new visual here that just shows, okay, if it's spreading out from a point source, yep, each square is going to have 1/4 of the amount of lines going through it. And you kind of think of that as the strength of gravity, maybe a graviton. I bet we'd probably bring that up with students, but we got this new walking the triangle slide. And then I will show, they can put it in their toolbox if you're doing that. And then here is the universal gravity poster. So I'll close that, and we'll go back to the Desmos and hop back in, and I'll throw it back to Matt.
Yeah, so we just wanted to highlight just a couple of slides from the Desmos. not go super in depth to any of them, but we want this is a new pattern and one that they are um, unfamiliar with, but there's a lot of similarities and differences, and so we want to just have them start by comparing and contrasting the new patterns, um, the inverse squared with the inverse and the quadratic pattern, and just give them some time to play around with this new mathematical model that is um, unfamiliar, but uh, but is just a combination of other math models that they've seen. So um, we wanted them to start with that. And the nice thing about Desmos Classroom is that it can provide feedback on the teacher end as students are working through. Um, Bedford, if you go to the next slide. There's also just like some time for us to, dig into our pattern. And so we're not going to show the simulation, but it's a PhET simulation that does a good job showing how masses of different objects affect the force. And so they're they play around with the different variables and see what is affecting the force, and really come to that idea of the mass, increasing the mass of either objects, um, or decreasing the distance between the objects increases that force that's there.
Maybe I'll jump in here quick. And
Yeah.
the other overview comment is we've hit the big idea now between this and the poster. All the remaining slides, and a lot of students are going to be grabbed by this, but I will just say a lot of them are in there to reach all of the evidence statements called for in the performance expectation. So you can see that it sort of takes a turn from the big idea about universal gravity and having the inverse square pattern. And then this dives a little bit more deeply into, and so that's the question. If you don't have a lot of time, you might, if you want to get to the big idea, you might want to jump back to the slide deck and we'll show just some of the other great applications that this has. But if you have the time, and really this does still fit in 2 days, but if you only had one day and you're worried about packing too much in, you have the option. People are always asking, if you don't have enough time, you're running out of time, it's the end of the year. This is a spot where you could start to cut it. With that, I'll throw it back to Matt.
Yeah. So, like Bradford said, lots of these are getting that to this idea of hitting those performance expectations. One of those or those evidence statements is like calculating the gravitational acceleration. And so one way that we did that was using modifying an application or a Desmos application here, and students can enter in a value. So this is acceleration or the strength of gravitational, and it will animate the jumper. And if you do that correctly, it will the ghost goes away, because the ghost is the correct jump, and then the one that's solid follows the ghost if it's matched correctly. So they do that jumping on Earth, and then on the next one, or sorry, the next, yeah, they're jumping on the moon. And so you can, if you put in 10, or 9.8, you can see a big difference in how that jump would look on the Earth versus the moon, versus I think the next one is for the sun. And so students can calculate the strength of the different gravities and then jump in on the sun. If you could, way difference. You can see that the ghost jumper barely gets off the ground as they're going. And so just a kind of trying to get that feel of, is that calculation correct? And is try to give a visual example of if it is. Yeah. And then,
Oh, yeah.
Yeah, go ahead.
Excellent. Just another chance to get students to actually write about their awe. So this is one that nothing magical about this prompt other than just we rarely ask students to write what do you marvel at with the universe? So it's been just a popular one among teachers to read the responses students give, and a wonderful one if you have the time for it. And then just completing that last little bit, the PE does want you to connect the inverse square law of universal gravity to the inverse square law of uh, Coulomb's law, the electric force. So there is a piece for that, but that's a far reach, and you really, if you have the time for it, it's good, and it's a resource there to you. But we do actually want to start to wrap up this task, but show some, and this is a video that we wanted to show a little bit, about 80% of this video, and maybe perhaps a new application to some people. Certainly, it's mostly new to students.
Gravity. It's everywhere. It's the force that keeps our feet on the ground and the moon orbiting Earth. But where does it come from? Mass. That's simply the amount of stuff that makes up an object. The more mass something has, the more gravity it has. Earth's gravity is constantly changing because something with a lot of mass is moving around all the time. What's moving? Water and ice. If you've ever picked up a bucket of water, you've felt just how much mass it has. It creates a lot of gravity. Using satellites, NASA can measure Earth's gravity like a scale in the sky. By comparing one month to the next, we can track where the water and ice is going. Weaker gravity means there's less water in that spot. This can tell us where a glacier is melting or a severe drought is drying up lakes. And stronger gravity? More water, such as in the rainforest in the Amazon. Our scale in the sky even lets us measure water deep underground. Knowing where the water and ice is moving helps us improve weather models, forecast droughts, floods, and wildfires. It also helps us get water where people need it. Measuring gravity from space helps NASA better understand the entire water cycle here on Earth. And that can come in handy next time you want a glass.
Okay, so this video, a lot packed into a minute and a half, and then just a real opportunity, to put it to students to what else could we think about? Good conversation starter. Yep, I think we decided not to show too much of this, but this is the Coulomb's law FET, or actually, this is the universal gravity FET. So there we go. All right, so we're going to transition, or actually we have a prompt here. If you want to write into the chat, going back to that idea that these are modular, or they can be modular. They're best in sequence. So if you do them all together, that's great. But just give a chance to have people say when, like we are pretty close in the year, but anyone see a spot or think about how they might use this end of this year or even the beginning of next year. I'm going to close these, and I'm not sure what's going to happen if I close the final. Yeah. Okay, so I'm going to reshare the screen. And I lost my chat in that. Yeah, preserve them as a unit. That is ideal, especially if that works. Okay, so we are going to move on to the second task in this series around orbital motion, and maybe it's worth reading the performance expectation. Use mathematical or computational representations to predict the motion of orbiting objects in the solar system. And again, we'll try to call out, there's a couple spots that we dive a little bit deep into Kepler's laws, and that is when if you're always short on time, what's the thing to cut? We'll call that out, but just know that those things are there as a resource when you have the time for them.
So,
Yeah.
so just to start off a really cool demonstration that we do, that we have a video for, is just trying to bridge that like universal gravity, thinking about orbits, or sorry, universal gravity from a test before, thinking about orbits, and then this gravity well demonstration. And so this is pretty cool that you have a hula hoop and some stretchy like spandex material, and then it's clipped on. We don't put it on stools like that. We have students typically hold on to it, though it's nice to have it level. And the big idea is that if you put a mass in the middle, maybe the mass is acting like the planet or the sun, you can see that an object will orbit around. And so this is doing a good job of showing that orbital well and showing that orbital motion. And there's just some observations you can make from it that, sometimes it looks circular, but a lot of times it looks elliptical as it's going around that. And we just came off of Halley's Comet, and sometimes when you do that, you'll actually see it. It'll be comet-like. It will come in close orbit and then move from there. So these two, or there's 3 different videos of it, and they do a good job to be able to show like over the top to everybody. But this one is just honestly a lot more fun when students are involved in holding things. So we have a bunch of marbles that we do this with, the ball bearings from earlier in the year, and you can see the orbital motion that happens there. And then some cool like unexpected things happen too. You can get let's say the sun is in the middle, and you can get a planet, and you can actually have a moon that orbits around that. So these ones are just kind of cool, cool demo of just being able to see what is going on in that orbital motion with those. And of course, these gravity well does a good job, or these videos show a good job of what you can do with it with students there. Good. And then, so with that, like we start with this demo, and we really want to kind of bridge the gap between this orbital motion and thinking about the cross-cutting concept of energy and how that plays into it. And that really goes into the Desmos classroom activity that we've created to do that. And I'll hand that over to Bradford to talk about.
Yeah, excellent. Thank you. Yep. Don't want to lose you in the slides, but just do want to show that there's a slide for each of the big moments that we want to talk to students about. So just as Matt just mentioned, we're going to transition to a Desmos classroom activity, which actually just got rebranded to Amplify Classroom. Everything's going to remain free and open, so all the links will stay the same too, in fact, but you will start to see the language Amplify Classroom popping up. All right, so with that, let's take a peek at the orbital motion. And here, we just want to tie the energy analysis that they did in Unit 2 around the bungee jump to orbital motion. So let's start simple, build the complexity. So we revisit the energy skate park, and at position 1, they don't have any kinetic energy, but they have a lot of gravitational potential. And this is qualitative, just like we started in the beginning of Unit 2. And then at position 4, up here, I'm reading position 4, it has about what, I don't know how high, 2/3 of the energy or 70%. In any case, the important thing though is we know it has some kinetic energy when it does get to 4, but the total energy remains the same. And then so now when we go and look at gravity in orbits, they can see, and this would be active when they're in the gravity in orbits FET, but back here in the classroom, Desmos classroom activity, yet again, position A and position B. Position A, they're really far out, so they got a lot of gravitational energy. And since it is in orbit, we know that it has its orbital velocity. So unlike the skater, there's never a time when the orbiting object actually completely stops. So in any case, though, compared to position B, the thing that students know is, oh, it doesn't have a lot of gravity. They don't know what the EK is, but through some reasoning, oh, energy's conserved. So they start to say, oh yeah, that kind of makes sense. So that's just like throwing a ball up or a skateboarder on a skate park. When you're far away from the center of the earth, you have a lot of gravitational potential and low kinetic. And as you fall towards the earth in your orbit, that gravitational potential is transformed through the force of gravity to be kinetic motion energy. So that's the real big connection point. And if students see that connection, that is just a great application of the cross-cutting concept energy, and they are set up for success. So we don't want to skip this. If they don't see this connection, all the other slides are going to be difficult. If they see this connection, each slide builds in rigor, understandable rigor for most students.
Bradford, can you
Then,
go back 2 slides really quick? Um,
yes, uh,
or
it-
actually, it's forward now on this
yeah,
slide deck. I just wanted to show, click on that simulation back one.
back-
Some people are familiar with it, but some people
okay.
aren't. That they're not going into that like without seeing this before. So we give them time to play around with this gravity and orbits simulation. There's lots of different various scenarios to do. Um, you can change the velocity of the object that's orbiting, and so just having these different experiences before they're playing first and then making close observations and then uh, trying to get into the science of it, that they have experienced orbits twice so far. They did it looking at the demo that we did, and then also looking at this. So just wanted to jump in and call those out.
Excellent.
Oh,
Thank you for doing that. We were going to show up to 11. Yep. So we got that one. And, at the end, we want students using the big ideas of science to explain phenomena. We will call this out. These next couple were what we talked about with connecting, really want students connecting to orbits with conservation of energy, just as we've already discussed. But the evidence statements call for connecting it to Kepler's law, which is excellent. It would be really the most perfect one would be to connect with your math teachers, because Kepler used geometry to understand this. He didn't have conservation of energy. So this is just that equal periods sweep out equal areas. And so when you're really close to the Earth, if you're going to have the same area, you need a really big base because the height of your triangle is very low. So that kind of makes sense that you have to be going fast to get that big base. And then as you're far away from the Earth in terms of sweeping out the equal area, because your height is so high, your base can't be that big in order to have sweep out equal areas. But in any case, just wanted to show you that that is there. But this, if you are short on time, you can lose students at this point. But if you have the time, it's a great one. And Kepler's laws are great to teach. And sometimes though, that might be something that if you teach an astronomy class, you might save those slides for that class and the deeper dive. Excellent. And then just wanted to show a couple, there's just, little fun tidbits. This allows students to make their own solar systems and just a few minute activity, but just want to show there's a lot of resources here to, this, as Matt said earlier, that this whole unit is trying to stoke wonder and awe. And just one last one, I'll keep it really short. But this is nice because it's a little bit closer to that gravity well. And of course, the gravity well is popular, but here's just a digital version. So anyways, you create by clicking the mouse, you make things, and then you can give them a velocity. And then if you still have the gravity well set up, you can try to, you can move between, probably only have one gravity well in the classroom. This gives every kid in the classroom a chance to play with it. And then you might move, you might try something here and then try to recreate it on the gravity well. As we get towards the end of this task, I want to step back and I'll throw it over to Matt to just what are any closing comments, and then I think I have one, but I want to sync it up. So, Matt, anything that I missed
Yeah,
you want to add?
again, this is just building on that idea of spiraling through energy, energy being such an important concept, a cross-cutting concept, and multiple performance expectations as well. And so we lean really heavily on their understanding of energy. And so, like we said, like this one for sure needs to come after Unit 2. And Unit 2 is so early, so because there's so often that it's helpful to think about the energy of a system before. And so, coming back to this with orbital motion, thinking about orbits, thinking about energy that's there, and using that cross-cutting concept to really explain what's going on through the orbit is just a really powerful tool that students can use to understand something that's really big.
Yep, excellent. And just here's a peek, and I wonder maybe I should. I can't with the Zoom is blocking it. I was going to try to show multi-slide view. I guess maybe. Anyways, you can just see it on the left bar. Sorry that it is probably smaller. I don't see the easy way to just show a peek at. You can just see that each of these, like there are slides here that allow you to, anytime that we're asking you to facilitate a discussion while they're in Desmo's classroom, there's a slide that accompanies it. And then just again, just to show some fun, not in the performance expectations, but students that are interested in astronomy will likely have heard of dark matter. So here's a chance to talk about it. There's a great video right here that I don't think we'll play in the webinar, but then just lots of application questions. There's always that question about what about the killer asteroid and Artemis. We actually, yep, you can just tell this is loaded, so we're not showing everything, but the Artemis missions are what we have our common background question with. And then after having done this activity, return again to the Artemis missions and then space junk and solar storms. So just high interest things that, catches some students. And again, not every student is interested in solar storms, but it's certainly grabbing students that might not have been grabbed by some of the other things. And it's just grabbing a lot of students. A lot of students don't know this, but it's just sort of kind of, space wonderful and does tend to grab a bunch of students. So we want to take advantage of that. So those are the resources for task 2. We did want to, maybe it's a pause, and if you want to write it in the chat, that's really nice. It's nice for us to be able to read it, but just want to pause here and say, what gets you excited? Trying to think about these units, the NGSS, Earth science, astronomy. Is there anything that you've seen here? We're oftentimes saying celebrate the positive, and we're asking students the same question too. Of like, what got you excited today? Just giving them a chance to relive something or bring it up to the front of their mind. Yep, I see.
I'll just say, like, for myself, it's so fun. Like, I think astronomy captures a lot of students, or astrophysics captures a lot of students that like just a wide range. There's a lot of students who have awe in this and have a lot of questions and really want to like dig into what's going on in space and the universe. And so just a lot of fun conversations that students have in this unit.
Excellent. So want to keep this pace up and look at our final task in this unit, and that is the one around constructing an explanation of the Big Bang theory based on astronomical evidence of light spectra, motion of distant galaxies. And this last one is a doozy, composition of matter in the universe. So just be ready for that. So we want to, you're going to see, this is a stations activity. We tried to have stations. We don't want them in every unit. Any strength overplayed becomes a weakness and students kind of get too much of it, but we do use stations in almost every unit. So I think they start in, actually I'm blanking on my head if we have them in unit 2 or not, but definitely have them in 4, 5, and 6. So we're about to give an overview of this task 3 and just lead with stations allow that joy of bite-sized learning. It really allows the teacher to be the guide on the side. And especially in this unit, students have just, like, whoa, I never thought about that, or that is so weird. And they oftentimes want to talk to the teacher about it and bounce ideas off of you, ask you follow-up. So really great. And then this is another one that just a real chance to inspire awe. And we have it here. So it's definitely worth calling out that this, again, scale, right? So it's not too often, chemistry, it's really easy to talk about scale. You're going down to the atom. Physics is somewhat easy. There's many times scale shows up, but the universe is just a prime. That's probably one of the best spots in the whole year to talk about scale. So you'll see several videos on scales, zooming out on, from the Earth all the way up to the solar system, the galaxy, and multiple galaxies. All right, with that, I need to switch my.
Yeah. And I'll just say, talking about the Big Bang, this is something that when we were, that I had to learn a lot about. And so we wanted to start with showing a video, just in case you don't have background, thinking about the Big Bang and all the pieces that go along with it. Some of these videos are a bit longer. I think the one that we'll show is not too long, but just gives a good background. And then the goal of the stations is to, break it down on all the little pieces that students need to know to be able to understand how does this work. And so we're going to start with a video to just show you. There's lots of great videos out there about how the Big Bang works, but this is one that we chose for the length for the webinar today.
Yeah. And we don't, it's going to go more than what we need. So I do want to, we'll start with, they have a paper-based packet for these stations, just like the other stations, just to be clear here. So, here's the guiding question. What is our universe and what do we see happening? So this is that idea of, when you talk about universe, the first thing we usually, when she gets past the solar system, is thinking about the Milky Way, multiple galaxies, and then zooming really far out. We're not expecting students to know everything in this video. It's mainly just getting kind of like blowing their mind a little bit. So with that said, I think I got this working.
There was a time when the universe was expanding so rapidly that parts of it were moving apart from each other faster than the speed of light. That time is right now. A lot of people make a big deal out of the fact that during inflation, right after our universe burst into existence, the whole universe was expanding faster than light. Now, while that is true, it kind of implies that the universe doesn't normally do that, and it does. I mean, if you pick 2 points far enough apart in our universe, you can always find ones that are moving apart from each other faster than light. That is simply due to all of the expanding space in between. So, our universe is now and has always been expanding faster than the speed of light. But doesn't this violate Einstein's special theory of relativity that says nothing should be able to move faster than light? Actually, no. Relativity says nothing can move through space faster than light, but that doesn't stop space itself from expanding however it likes. Now, it was Hubble in the late 1920s who made the observations of the night sky which led us to see that our universe is expanding. The further out in space he looked, the faster the objects were moving away from us. So imagine a point so far out there that the average recession velocity is the speed of light. I mean, if you think about it, it's going to be the same distance in every direction. So that would form a sphere, which we call the Hubble sphere. Everything beyond that sphere is moving away from us faster than the speed of light. So common sense would say we would never be able to see the light from those objects because of how fast they're moving away from us. But in fact, this is not true. We can see those objects. To understand how this could work, picture a galaxy beyond our Hubble sphere. It's receding faster than light. It's in a superluminal region of space from our perspective. So any light that emits in our direction will actually be moving away from us as time goes on. Well, that doesn't sound very promising. But due to the accelerating expansion of space, our Hubble sphere is actually getting bigger. And if it gets bigger faster than that light can get away, then at some point that light is going to travel from a superluminal region of space into a subluminal region of space, and so it can start making progress towards us. So we can detect it, so we can see that distant galaxy, which is of course now even further beyond our Hubble sphere, but we can see its light. We can detect that it's there. This is remarkable. In fact, all of the photons we now receive from the first 5 billion years of the universe, they were all emitted in regions of space that were traveling at the time faster than the speed of light relative to us. The objects that emitted them were, are, and always have been moving away from us faster than the speed of light. But their light has entered our Hubble sphere and had enough time to reach us, and so we can see them. So the observable universe is larger than our Hubble sphere. It's actually limited by what's called the particle horizon. That is based on the amount of time light has had to travel towards us since the beginning of time. That is 13.8 billion years ago, as far as we can tell. Now, because the universe has been expanding and that expansion has been accelerating, things are much further out than 13.8 billion light years away. I mean, the observable universe has a radius of over 46 billion light years. The diameter is about 93 billion light years. That is a huge volume of things that we can see. And 13.8 billion years ago, everything in that volume and everything beyond it that we can't see would have been compressed into a tiny, infinitesimally small point that we call the singularity. Actually, no. I mean, that would be true if the universe is finite, but if the universe is infinite, and it kind of looks like it is, then it was always infinite. So the Big Bang would have happened literally everywhere. But if the universe has always been infinite, then what is it expanding into? Well, it doesn't have to expand into anything. I mean, it can expand into itself. That's the thing about infinity. You never run out of it.
Okay. I don't know exactly your reaction, but that blows a lot of students' minds. There's a lot of questions. In fact, sometimes there's a lot of silence of like, what? What did I just like? How did I take that all in? I'm trying to get out of there. Okay, excellent. So that's in one sense both a showstopper and a conversation starter. So there you're gonna see repeated themes. We're not gonna play this one, but we have 3 videos. And of course you're taking in questions in between. And again, just to that video that we watched doesn't get at this guiding question a little bit. You know, what is our universe? What do we see happening in it? But there is 2 more videos to kick us off, and then students watch and draw and respond. When I just throw it over to Matt, I didn't know if you wanted to say something, so I'll throw it over to you.
No, just the big idea is Station 0 is a station that everyone is doing together. So we're going to talk about the activity that they're going to do, but there's several videos just before kind of setting the stage. And then uh, once they have, once we've set the stage um, and done an activity, which we're going to talk about soon, then we go into more traditional stations where like they might be going from station to station and learning those things. So just the aspect of the activity is building all of that.
Yeah.
Bradford, do you want to click on the next slide over, next
Yeah.
tab over?
Yep.
So our big goal is to highlight a couple, like one thing from each station and explain, you know, what students are doing and how they're making sense. And that leads us to the first station. And maybe come back to this station and go to the next slide, or sorry, come back to this slide and click one tab over. So this first station again is meant to a little bit inspire awe. And so we set up a two-scale model of several galaxies in the universe. So some of them are closer, some of them are further away, and we have a football field scale. And then if you click to the next tab, like just go, sorry, go back to it and go to the next, like click next on there, with like a classroom setup. And there's measurements down that you can see down linked at the bottom. And at each of those locations in the classroom or on the football field, we put a placard representing the universe. And so, yeah, maybe zoom in on it, Bradford.
Trying to do them.
Yeah,
Super
sorry.
hard to see, but you just see the posters, they're hanging by string from the ceiling. So the purple or the pink circles, and you can see they're in 3 dimensions. And with that, I'll throw it back to Matt.
Yeah, so that this is a, you know, classroom setup of what it might look like. So if you go to the next tab over, we will have a zoomed in look of what it looks like. So I go left one, yeah,
Left one, yeah.
yeah. Yeah, on each of those placards, which we print in color because they're just so beautiful, is you know, a drawing or an actual picture of the galaxy. And then on the back page, go ahead, click once, it has some information that they're going to gather. So um, they're going to measure the distance and the brightness of things in the galaxy, and it's given to them. The brightness is there, and they're going to be able to measure the distance. And we'll talk about like, how does brightness show up? What is a standard candle to be able to find how far away things are? But of course, the Milky Way is where we are, and so there will be no distance. Like they're going to measure distances from the Milky Way. And then for velocity is the relative speed, so it's given to them. And there's a redshift that happens, which students don't know what redshift is yet. That's one of the stations. So another example, Pinwheel Galaxy, you can see its brightness, it's dimmer, it's further away in the same way that a flashlight is dimmer when it's further away. And we've got this relative velocity, and you can see that there's some redshift going on. Again, students don't know yet what redshift is, but that is on purpose. That's one of the stations that's there. And then, yeah, go to that next, the worksheet there. And on there, yeah, go ahead.
I was just going to say, to contextualize this, we made this up so that there was a hands-on activity, and it's super fun. But in one sense, these are all numbers that are known, but to bring a like do something yourself, we make them actually, instead of giving them the distances to these galaxies, they get it by using a tape measure and measuring in meters and then converting to the actual distance. So it's a little bit, you know, artificial. It's real data, it's accurate data, but we wanted kids moving around the football field, the the classroom, super fun. And again, it's just that chance um, to have the teacher on the side and lots of activity. So if you're just kind of wondering like why do this, it really is just for the joy, the fun of getting out tape measures and measuring it to make it more interactive.
Yeah, and you can see at the bottom, it's hard to see, but it says the node of the field scale. So like 1 meter is measured out to be 5 million light years, and so they do the tape measure part, and then they go and actually calculate the distance. And in the next station, we'll talk about what they're gonna do with the data, and maybe I'll hand that to Bradford to talk about the next station.
Yeah, great. And we have the slides, but just to show you in the paper based. So yep. So here's station 1. How does the distance a galaxy is away affect the velocity of the galaxy? That's in multiple videos already, the one we watched and some of them that we didn't. But of course, this is them finding Hubble's constant. All right, so this is again, just want to show how approachable this is. So like the videos can make you feel like, whoa, students could be overwhelmed. And just want to say from experience, it's mostly fun. Students just focus on the part that is blowing their mind. And then of course, we do want that good science education too. So these things target it. And not to sound repetitive, I just want to say that Redshift, it shows up like 3 or 4 times in the stations because it's so important, right? That was in the performance expectation. So it's repetitive on purpose because one vantage point, one way of thinking about Redshift isn't enough for most students to really feel confident. So we want to give them a chance to build competency with these ideas, which means multiple stations for most likely. Okay, so to take a peek at how does distance affect galaxy, just to look at one slide from it. And this is an excerpt. So they actually read, this is considered one of the most like readable scientific articles. So this is actually Hubble's paper that he first published the Hubble constant in. So actually have them read an excerpt from the actual paper.
Yeah, Bradford, before you click off of it, I think it is worth showing for this one because this is just like, Stearns again, go to the next slide if you don't mind on this one. So they are using their data that they took from the field to make a math model of the graph. How does distance affect the velocity? And it's surprising that the further away a galaxy is, the faster it's moving from away from us. And so that leads to like where is that coming from? Where's that going? And then they also like, they respond in every station, they respond. And maybe just click the next slide on this one more down, Bradford, where they respond in the same way. How does the galaxy affect the distance? Sorry, how does the distance affect the velocity of the galaxy? Here is what they do. So it's very much spiraling with the other things that we've done in the course. That leads us to station 2, and maybe show, if you don't mind, Bradford, the packet to show the question. Scientists believe space in itself is expanding. Like, what does that even mean? And so with this one, we do want to show you a couple of things out of this. First, we want to show you the video. And yeah, could you go to the tab to the right and yeah, just play that one.
The universe is expanding, so does that mean there's a center from which everything is stretching outwards? I mean, it looks like the center is here because this point didn't move when we scaled, but we could just as easily have watched the scaling from this star, or this one, and they each look like the center. In fact, anytime you scale anything up or down, there's no real center to the scaling. I mean, this square was clearly scaled up from its center. I mean, its corner. I mean, that point over there. The point is, sure, there may be points that stay in the same place because of your frame of reference, which is why it appears to us as if the Earth is the center of the expansion of the universe. But to someone in the Andromeda Galaxy, it would appear that they were the center of the expansion. In short, if you're too close-minded to view the universe from different perspectives, it's easy to think you're at the center of the universe. Maybe that's the universe's way of making us all feel special. But really, we're not.
And so this station is all about thinking about that idea. But can you stop yours or go to the next slide first, and then go out of it. Go to. So we have two other. We've got the video. We've got a Desmos for them to play around with. If you press the play button on the time, you can see like all of these galaxies are moving away from us. And then you can reset the time and shift point of view. So if you maybe turn on just slide it over to 1 and then do their point of view. You can see, and then press play. Keep that one off for now. You can now see, like, now the Milky Way is going away from the Sombrero Galaxy's point of view, and then we could look at somebody else's point of view, and everything's moving away from it. And so just the idea of your point of view is showing that you're the center of the galaxy. Then of course the last thing that we have is there's just another hands-on one where, and we tried this on video. We'll see how it works. If you could stop your screen share, Bradford, really quick. Is you just take a rubber band, and I didn't label my rubber band any of the letters, but like if I say, we'll see how this works. If I stretch from this middle one, you can see like one is, not doing a good job. One's moving, one staying still, the other ones are moving. If I go to a different one, everything's expanding away from that one. And so you're just getting another tactile feel for the space is stretching. And if you're holding one stationary, from their point of view, it's not moving, but everything else is moving away from it. So just getting those tactile feels of scientists believe that space is expanding. Like, what does that even mean? And so, that's station 2, and I'll hand station 3 over to Bradford.
Nice, thank you. And just to bring continuity, you go back to the packet. How does a car horn inform us about the movement of galaxies? Won't go as deep into this one, but just this is Doppler effect, and so no surprise, we will just. I didn't think we're showing this video, so actually,
was a lot smaller.
I'm trying to get past this video. Okay, so this one is one of multiple that hits at the redshift, right? That last rubber band expanding kind of showed that, okay, they're moving apart. What's going to happen to the waves that move between them? That is the redshift. So that one's quick. Moving along with all of these stars and galaxies. Why is the sky dark at night? I think I got off here. I was expecting when there's a video on there. That's station 5. What happened? Yep, this is it. So good. Yep, I will play this. This is short, so this.
Why is the sky dark at night? You might think the answer is obvious. The sun isn't up. But the only reason the sky looks blue during the day is that sunlight scatters off of the atmosphere. If we didn't have an atmosphere, like on the moon, the sky would always be dark, even when the sun is shining. So let's rephrase the question. Why is space dark? I mean, space is full of stars, countless stars which are all about as bright as the sun. And in an infinite eternal universe, no matter what direction you picked, if you looked far enough in that direction, you would see a star or galaxy. So the whole sky should be as bright as the sun. night and day. And since it's not, does the darkness of the night sky mean that there's some distance away from us when stars and galaxies just stop? A boundary between something and nothing? An edge to the universe? Not exactly. All of our evidence seems to indicate that space has no edge, but the universe itself does. Not a spatial edge, but a temporal one. As far as we know, the universe had a beginning, or at least a time about 13.7 billion years ago when the universe was so small and crumpled up with itself that our standard notion of space and time breaks down. And since only a finite amount of time has passed since this so-called beginning, that means that some of the stars necessary to fill up the brightness in every direction are so far away that light from them plain hasn't had time to reach us yet. It's as if the universe were a big thunderstorm, and we're still waiting to hear the thunder from the really distant stars. But wait, it's better than that. Since light takes time to travel across the universe, when we point our telescopes at something really far away, we're actually seeing that part of the universe as it was when the light was emitted. So when we look at 13.5 billion-year-old light, it's not that we don't see stars just because the light from them hasn't gotten to us yet. We don't see any stars because we're getting a peek at the universe before any stars had formed. A starless universe. Now that sounds to me like a pretty good reason why we look up and see a dark night sky. But it's not. I mean, it is true that we can find points in the sky where there aren't any stars by looking past the earliest stars and thus farther back in time. But even when we point our telescopes past the earliest stars, we still see light. Not starlight, but the light left over from the Big Bang. We detect this cosmic background radiation coming more or less evenly from all directions, forming a background beyond the stars. So I guess the night sky isn't actually dark to begin with. Right. So if our telescopes tell us that the night sky isn't dark, then why does it look dark? Here's a clue to the real answer. When the Hubble telescope photographed the distant stars of the astoundingly beautiful Hubble Extreme Deep Field, it took the picture using an infrared camera. Why? Well, distant stars and galaxies are moving away from us because the universe is expanding. So the same way a record slowing down lowers the pitch of my voice, the Doppler effect causes stars moving away from us to become redder. And the farther away they are, the faster they move away from us and the redder they become, until they become infrared. And then we can't see them anymore, at least not with our human eyes. And that's why the night sky appears dark. In summary, if we lived in an infinite, unchanging universe, the entire sky would be as bright as the sun. But the sky is dark at night, both because the universe had a beginning so there aren't stars in every direction, and more importantly, because the light from super distant stars, and the even more distant cosmic background radiation, gets redshifted away from the visible spectrum by the expansion of the universe. So we just plain can't see it. Finally, we've shed some light on why the night sky is dark, and why it isn't.
Nice. So that's another great video. There's a lot of questions generated by it. And just to take a peek, trying to make it not just videos, if especially your chemistry classes and storeroom might have more likely this, but if you do have those spectrum tubes, on our supply list is the spectral glasses and just a chance to look so that when they look at that spectrum right here from those cards going back to station 0, that just they have a more tangible experience with that. Then Matt, I didn't know if you were waving to jump in.
No, I was just thinking about I'm here and getting to the last couple ones. So just looking at Station 5. Station 5 actually, I don't think it's worth maybe showing the video. But what direction should you look to see the Big Bang? That one goes specifically, just tails right on Station 4 in that video that we just watched. That it kind of goes through the story of how the cosmic background radiation was detected, and how looking out into space we are detecting this. And so there's a good video from Physics Girl of what is going on and where should you look to see the Big Bang. So yeah, that's a good one that kind of bridges that. This one is, let's see, is this the one? Yeah, actually go back one slide here, and then I think we do show this video. The question and for station 6 is, how do we measure how far a star is? We can't just take our measuring tape out, and so we use again what we call a standard candle, and I think this one is definitely worth showing because it illuminates how do we actually take the data? How do we verify that this is there? Yeah.
So type 1a supernovae, it's like the universe's free gift to us. Because they all explode in the same way, they reach pretty much the same brightness. So if you see one dimmer than the other, it means it's further away. And that allows us to measure distance to the galaxy that's hosting this supernovae explosion.
We have seen type 1a supernovae across the entire universe. We can measure the distance to their home galaxies. And that can tell us how the universe is changing over time.
So when we look at distant supernovae, we see something really interesting. Their light's not just dimmer, it's redder. And the further away they are, the redder their light is. But as the light travels from this distant galaxy to us, space itself is stretching. And so the light gets stretched along the way. It gets redder.
I am a little worried about our time overall.
Yeah.
So, but you can just see the recurring themes, right? Redshift. And then the one other punchline that this video does a great job of is saying why. Why are they a standard candle? And that's super neat. And I think for time we do have to just kind of say it. And that is, in binary stars, one star may go nova and have a white dwarf. And then it has a companion star still, though. And that when that star goes red giant or puffs up, it feeds its gas into, or plasma, I guess, into that original white dwarf. And when the last atom falls and makes it go supernova, it always blows up right when, like maybe not down to the last atom because millions of atoms are falling in, but it always explodes the same way. So that type of supernova always blows up under the same conditions, so it gives off the same brightness. That's a little bit oversimplified because there is like an angular dependence, but that allows it to be that standard candle. And then you also saw the redshift spiraled in that one. Just to give us a sense of closure, and we got several more stations to do here. So that one was, how do we measure how far a star is? And you can tell by the brightness of type 1 supernova, just with the analogy she gave in the video. They should all be equally bright if you were 1 light year from them. But if one is dimmer, it's because it's farther. Okay, and then how do we see the invisible? And again, we already heard that word infrared we've talked about infrared in the waves unit. So you can, and then we talked about it in the electricity power reduction and climate science unit. So lots of things are spiraling in the curriculum. So new ideas, but also reaching back and getting exposure with them. And of course, this is the James Webb Telescope. And that's beautiful, the beautiful pictures, that deep field with Hubble that was in one video. We now get James Webb took that same picture, and it's just beautiful to see James Webb take the same deep field in the infrared and see how it's different than the Hubble taking it in the visible. Quick check in with Matt. Yeah, this is great. And, literally new stuff is coming out every day with the James Webb Telescope. So if you ever keep your eye on news that's coming out, that's a great current event. But it does go to the story of how we see infrared. And just to bring continuity, or yeah, I'll throw it over.
This just a couple more stations here. Next station here, how big is the universe? I think we'll just like make a nod to, these things that um there's a couple of cool interactive activities where they're looking at the size of the universe and size of different objects in the universe. Um, so that's first. Uh, there's a kind of a cool video thinking about just the cosmic ruler, how we're going to measure how things are, and then they figure out, they basically are making a scale model. If the moon is one step away, how many steps away is Mars? How many steps away is the sun? So just kind of a good aspect of doing some of that proportional reasoning, doing some calculation for what, how big is the universe. Yeah, and then maybe I'll hand station 9 to Bradford.
Yeah, this one's loaded. This one is straight out of that performance expectation. This is a tough one. To be candid, we had to go and read up about it. I had a astrophysics minor, but it was not at the tip of my tongue to have all of these stats. And really, we got it down to a 2 paragraph, and you really got to read in the details, but just because that is explicitly called out for in the evidence statements and even the performance expectation itself, and just to quick show that's that last piece right here. They explicitly call out the ratio of 3 times as much hydrogen to helium. When you look away from stars, there is 3 times as much hydrogen as there is helium. So that ratio, 75% hydrogen. Of course, stars are changing that mixture as they fuse hydrogen and helium into all the other elements in the periodic table. But in any case, it is pretty neat. I mean, like, as long as we don't lose students, that they just realize that, oh my gosh, in the very early universe, it was so hot that protons and neutrons didn't even stay together. And then it cooled off, which is still extremely insanely hot. Protons and neutrons formed, and it was hot enough to have fusion. That's the really neat thing. But it was so hot that, let's say an oxygen did form by chance, it was so hot it would get hit by another hydrogen and it would break back apart. So that early universe was just so hot that maybe oxygen never, that's pretty unlikely, but maybe 1 or 2 or something like that. But lithium probably got formed, but it got broke apart. And so lots of things were forming and breaking apart. And then, of course, it cooled off and dropped below the temperature that fusion could happen. And, it froze out in that ratio, roughly 3 to 1. And that can be seen in the cosmic background radiation. So that one, it's always a little bit of a reach to have students include that one in their arguing from evidence about the data that supports the Big Bang, but it is just 2 paragraphs. It is one that when students use their imagination and try to think about the craziness of that early universe, it is largely meant, we lean in on the joy of it. But just to be clear, what's the universe made out of? The big punchline, away from stars, 3 to 1 ratio, hydrogen to helium. Okay, getting close here. Oh no, I lost the, sorry. I closed the stations. And so anyways, got it reopened here. And then our last one, this one is fun. And of course, this just happened. So we used to only have 9 stations, but a couple years ago,
Matter as we know it.
Oh yeah, that had a nice dark energy connection at the end of what's our space, what's our universe made of, and yep. So I'm just gonna skip that though and say that now, literally in the last couple of years, through this video does a great job, and it is 4 or 5 minutes, but it does a great job of taking a picture of the center of the Milky Way galaxy, the gigantic black hole at the center of our galaxy, Sagittarius A star. So that is super neat and relatively like a current event. So we did add that station what is at the center of our galaxy. And of course, it's always fun to be talking about black holes. So that one is kind of a high energy one. And you know, it's always never know exactly which students, but there are students that have watched science videos that have read about astronomy and they know about this one. And it's you know, I call it a good thing when students ask me questions that I have no idea about. And you definitely are going to get some of those in this unit that they've seen a video or they've read something or they've thought about something, and it's impressive how far they've taken it. Okay, just to bring some closure to this, where all of this is around construct an explanation of the Big Bang Theory based on astronomical evidence of light. You know, that's that redshift, the motion of distant galaxies, that's that expanding universe, that those type 1 supernova are dim, and it perfectly correlates with the redshift, and then that composition of matter, that there's that 3-to-1 ratio of hydrogen, helium, and like microscopic amounts of lithium and other things. All right, so those are the 3 big ones, and hopefully you see those stations, get students pretty ready for it. I think we're in the all slides. Maybe one last peek as we start to wrap up to look at the learning plan. We've been going to the webinar agenda. So again, we had Halley's Comet, orbital motion, and then here's all the stations. I'm going to get ready to throw it back to Matt to just say any last comments, but it finishes. I was going to open the slides, but might even run out of time. You know, we do a stronger, clearer to before students write, and right here, stronger, clearer before they write. And then there's just some really fun bonus, you know, what are different possibly imagined ultimate fates of the universe. This is excellent, and it's behind a paywall, or it kind of cycles, but I think we might have found a permanent link. This is just another, you know, if you have a longer time, this one, you know, you can show a half hour of this Nova origins back to the beginning. Lots of, it hits all the things we just said. Literally, the thesis of this Nova episode is the evidence of the Big Bang. So that's excellent. And we didn't call it out in task 1. Each of these tasks do interlink at the end. Dark matter connects Halley's universal gravity with orbital motion, and then dark energy, whatever that is, does also connect universal gravity and this not understood idea of why galaxies are accelerating away from us. Okay, with that got almost all of my thoughts. Just want to bring some closure to this though, and let Matt kind of hit anything I missed or any sort of like broad last comments to wrap this up.
Yeah, I would just say like whether you're doing this unit modularly, you know, through the year or all at one time, we've done it both ways. We've heard other teachers doing it both ways. It's just a you know, fun unit to bring in throughout, or for us towards the end of the year, what we're going to do this year. So lots of cool resources, lots of cool videos that are there that are just extensions of the different things that we're doing. So yeah, I'm gonna go ahead and stop the recording here.